Say that again. Okay, so welcome to class, guys. Today we're starting a new chapter. This is the chapter on functions, and the material for today is quite important because pretty much everything in chapter 3 will depend on it, right? So we have to have a really good understanding of the various ways to represent a function, and there are many, and sort of how to use this function notation. Function notation will be the more important one, but if you want a conceptual understanding of what's going on, then you need to know how to sort of transfer back and forth between these various versions of what's meant by a function. Okay, so before I give you the technical version that the textbook uses, they call it a relation first. I'm going to sort of give you the picture that I have in mind when I think about a function, okay? So when I think about a function, I think of sort of like a black box, some sort of machine or some apparatus, and we'll typically label the box with some letter. So in this case, this is the function f, and there's some machinery in here, right? There's some sort of computation, or think about it maybe as a calculator or something like that. There's some process that's going on inside the box. And what we're given is an input. So there's an input into this box here. And when you throw an input into the box, it goes through this process and chugs through all along whatever this f is. And what we get is an output, okay? So we get an output here, which we label in this form, f parentheses and then x. And we call that output f of x, right? So it's not f times x. A lot of people confuse f of x as f times x. It's not the same thing as f times x. In this case, it's the output f of x. And the input here is typically taken to be the x. Okay, so you throw this x into the machine, it runs through some process, and then it outputs the function f of x. And the key feature of a function is that if you throw the same input in repeatedly, right, if I keep throwing the same input in, then I'm going to get the exact same output every time. There's no random process in here, like somebody's not rolling dice or something like that to figure out what your output is. It's all deterministic, right? You throw in the x, and then out comes the f of x. This collection of inputs is called the domain. So the things that you can throw into your machine is called the domain of f, and the things that come out of the machine is called the range. And on Friday, we'll talk more carefully about the domain and range, because not everything can be put into the function, and not everything comes out of the function. It may be the case that you only get even numbers or something like that when you're dealing with this picture. But this is the picture that you should sort of have in mind conceptually when you're thinking of a function. Now, the way that the book will word this is they'll think about functions as being relations, and a relation is just some collection of ordered pairs. So the way that this is getting back to an ordered pair is if you give me the input x, then we denote the ordered pair like this. F of x. So the input is x, the output y is f of x, and so often we'll write this formula as y is equal to f of x as well. This is also a really nice way to think about things because we'll just sort of write down a formula for f of x instead of sort of thinking about it the box. The formula is sort of the process that you go to get to the outside of the box. But the technical definition is looking at ordered pairs in the plane. So let's get a little more detailed with that. And I did things a little bit differently than I normally do. Normally I talk about the learning objectives, but let's talk about them now after I've sort of given you a quick little introduction into functions. And by the way, this is what we'll be talking about for all of Chapter 3. So all of Chapter 3 is all about various types of functions and how to work with them. Okay, so the first thing that we need to do is determine whether a given relation represents a function. And this sort of sounds simple on the face of things, and there's a really nice way to do it graphically called the vertical line test, but there are many ways to represent a function. So we'll have to talk about all of the different ways that we represent a function and how we can determine if that relation indeed represents a function. In terms of the affinity homework, most of the questions are about finding the value of a function. In other words, evaluating the function. So if I plug in something like 2, what happens with the output f of 2? Okay. I'm not sure if we'll get enough time to cover, like my last class, we didn't actually cover one-to-one, so we may say a couple of things about it, but there's nothing in affinity homework about one-to-one, but it comes up later in other sections. So we may have to cover that when we get to that section. We'll talk about the vertical line test and how we use it to identify if a graph is a function. So a graph is a particular type of relation, and there's a nice sort of graphical method, the vertical line test, that can tell us whether or not a given graph represents a function. And then finally, the last thing that we'll talk about is just a list of functions you should sort of know the shape of. And later on, we'll talk about transforming these functions, so stretching them and squeezing them, translating them up and down, left and right. And so this library of functions and the shape of the function will be incredibly important, right, in those sections. So we'll talk a little bit about some functions that show up. And again, as usual, I'll leave this up for anybody that might be writing it down or have a question. And if you guys are done with it and you're ready to go on, just give me a thumbs up. And when enough people do, we'll go on to the formal definition of a function. Okay, so let me erase this, and I think before I tell you the formal definition of a function, I need to tell you what a relation is. So I'll just do that on my blackboard, because this is not nearly as important, right? The idea of a relation is not going to come up nearly as much as the idea of a function, but I'll put it here because there are at least a couple questions along these lines in Infinity. So a relation is a set, is a collection. Set's the same thing as collection. Is a collection of ordered pairs. Okay. Any collection of ordered pairs whatsoever forms a relation. And there are many different ways to describe a relation, right? You can describe it with an equation, you can describe it with a graph, or you can just list out the ordered pairs in this relation. So here I'm going to do just that. This is called roster notation for a set. And I'm going to list out the collection of ordered pairs that are in this relation. So in this relation, we have the ordered pair 1, 2. We have the ordered pair 1, 3. And we have the ordered pair 2, 5. Okay, and this is just an example of a relation. And we could graph this relation as well. It would just be 3 points in the plane, right? They would all be in that first quadrant. So we could actually think about this graph. It wouldn't be a line or a curve or anything like that. It would just be 3 points in the plane. And anytime we have a relation, we think about the x-coordinates as being the input. And the y-coordinates as the outputs. Okay, so here our inputs would be 1, here the input would be 1, here the input would be 2, right? So the x-coordinates are the possible inputs into our function, and the y-coordinates, in this case the 2, the 3, and the 5 are the output. Okay, so that's how we'll think about it in terms of that machine. So what this first one is saying is if you plug in 1 into the machine, then the output will be 2. This one's saying if you plug in 1, then the output will be 3. This one says when you plug in 2, the output will be 5. Okay, so the x is the input, the y is the output. And before I ask you whether or not this is actually a function, let me give you the definition, right? So we're going to sort of think carefully about what the definition of a function is. Remember, a relation is just a collection of ordered pairs, and a function is a special type of relation. So a function is a relation in which each possible input value leads to exactly one output value. Okay, and we say in that situation that the output is a function of the input. Okay, so each input leads to one exact output. And here we call the input the domain and the outputs the range. So that's what I was saying before in that picture as well. Okay, so in the chat, chime in with whether or not you think that is a function. So if you think it's a function, say function. And if you think it's not a function, you can just type in not a function. And we'll talk about what the answer is here. So it's not a function. Okay, great. So everybody sees this is not a function. And the offender here is this guy here, the 1, right? So in this case, we plugged in 1 and we got 2, but then we plugged in 1 again and we got 3. So we plugged in the same input here and the output was different, okay? So this is not a function that we would, or this is not a relation that we would call a function. Now, there's a nice graphical sort of way of seeing this, right? So not even in the plane, but there's like a sort of nice way to describe what's going on here so that you can see the difference. And this is another way to represent a function. So in this case, we'll write what the domain is on the left, and we'll write the range on the right. Remember, the domain is the set of inputs, and the range is the set of outputs. Here, the inputs were 1 and 2. So we've got 1 and 2 here, and the outputs were 2, 3, and 5. Right, so these are the x values, these are the y values. And the first one said 1 was going to 2, and the second one was 1 was going to 3, and the last one is 2 is going to 5. And again, the problem is that we have 2 arrows coming out of one input, right? We don't know if we should go to 2, and we don't know if we should go to 3. In other words, if we were using function notation, we really don't have a good way of saying what is f of 1 for this picture, right? We wouldn't even be able to use function notation. So this is, again, not a function. There are going to be lots of questions, I think maybe like 3 or 4 in Infinity, where they give you some collection of ordered pairs and they ask you whether or not it's a function. The easy way to do this is just to check to see if there are any repeated x values. If you have a repeated x value, it's not a function. If there are no repeated x values, then it will be a function. Okay, so let's look at this picture now. And we see like some functions described in the same way. So now I'm sort of putting the domains on the left and the ranges on the right. And we want to look at what's okay and what's not okay. So like we said, if we have one input, for example, Q here, going to 2 different outputs, Y and Z, then we're not a function, right? So here, it's not clear what f of Q would be. Is it Y or is it Z? So this is not a function. If everything gets matched up sort of in a really nice way, in a one-to-one way, right? So P gets matched up with X, Q gets matched up to Y, R gets matched up to Z, well then clearly it has to be a function, right? So every input's getting mapped to one thing. But you have to be careful. Okay, so again, this is a function. But you have to also be careful because you can have 2 arrows going to the same output, okay? So for example, this first relation up here has 3 inputs, P, Q, and R. And both Q and R lead to the same output N, right? But notice that there's only one output for the given input, right? There may be 2 different inputs for a given output, but for a given input like Q or R, there's only one arrow coming out of it. So this is an example of something that is a function, right? So this is not okay, but this is okay, right? Having 2 arrows coming in is perfectly fine. And a lot of functions have that feature. Okay, later on we'll talk a little bit more about what this is on the left-hand side, and this is something that's not one-to-one. But we'll sort of come to that road in a moment. Okay, and then I guess there's another way to describe a function, right? So let me just talk about the last way to sort of maybe describe, I guess not a function, but a relation. So another way to describe a relation is just with an equation, okay? So in this case, it's going to be an equation in terms of x and y. So let me just give you a quick example of something like that. So let's look at y cubed plus x squared is equal to 1. This is an example of a relation. Okay, it's a collection of ordered pairs, and the solutions to this is the collection of ordered pairs that forms the relation. For example, if I were to take x to be 0, and y to be 1, then that would be a solution. So this is on that relation, right? Or this is in that relation. You could also have something like x is 1 and y is 0. And again, you plug in 1 for x here and 0 for y, and you'd still get something that was true as well. So both of these ordered pairs are on the graph described by this equation, and there are infinitely more, right? And we're going to be interested in whether or not something like this forms a function as well. And the way that we determine something like this forms a function is that we either graph it and use the vertical line test, which we'll talk about in a moment, or you just try and solve this equation for the output and hope that it's uniquely determined in terms of the input. So let's try to solve this equation really quickly for y, right? So here the question is this relation a function? Okay, it is a collection of ordered pairs, but the question now is, for every input, is there one unique output? And you do that by solving for y. So you'll subtract x squared from both sides. And we get y cubed is equal to 1 minus x squared. And then we want to undo that cube. So what do we need to do to both sides to undo the cube? Yeah, we want to raise it to the reciprocal of this power, which is 1/3. And that's also the same thing as taking the cube root. So we'll take the cube root of this side, and we'll take the cube root of this side. And that's a 1 minus x squared there. So we're taking the cube root of both sides. Do we need to add a plus or minus? So do we need to add a plus or minus? Okay, some have said yes, some have said no. The answer in this case is actually no. And the reason why is that we're taking a cube root and not a square root. And the general rule is that if you're taking an even root, right, if this number is an even number, you'll have to put the plus or minus. And if it's an odd number, then you don't need the plus or minus. And this is partly because a negative times a negative is a positive, and a positive times a positive is a positive. But anyway, we don't need to put the plus or minus here. So the cubes undo one another, and we're left with y is equal to the cube root of 1 minus x squared. And you'll notice there's no plus or minus here, so this is a function. You give me the value of x, and I can plug it in, and I'll tell you what the value of y is. Okay. So this thing is certainly a function of x. Notice that we can't plug everything in. So I can't plug in something like x is equal to 10. So the domain isn't all real numbers. We'll talk more about domains in the next section. But here it's certainly a function. You give me the x value, you plug it in, you get whatever that y value is. Now, if this would have been a square, then this would have been not a function. And the reason why is that we would have taken the square root here, we've got a plus or minus, and we wouldn't know what the output was. In one case, it would be positive, in another case, it would be negative. So we'd have a given input x with two possible outputs for its y. So if we were to take the square root there, we would get something that's not a function. So in terms of just an equation, if you can solve for y uniquely in terms of x, then it's a function. And if you can't, then it's not a function. And there are a few questions like that in Affinity. Okay, so that's another way to describe a relation. And let's sort of talk about the general method here, right? So how do we determine when a relation is a function? So somebody gives you a relationship between two quantities, either an equation or a list of ordered pairs or a graph, and you'd like to determine if that relationship is a function. The first thing that you need to do is identify what the input values are. For most of our examples, the inputs are just the x's, but there are some cases when that's not the way it works out. But we need to identify the input values. We then need to identify the output values. For most of our examples, it'll be y, but that's not always the case. There are some cases when a function uses different inputs and outputs. And we ask ourselves the following question, or the following if-then statement, right? So if each input value leads to only one output value, we classify the relationship as a function. And otherwise, we classify it as not a function, right? So if you have one input going to two possible different outputs, then it's not a function. And graphically, there's a super nice way to see this. If we're thinking about ordered pairs, the easiest way to do this is to look at the graph, right? So remember, a graph is just a collection of ordered pairs, and you draw vertical lines, right? So you draw vertical lines through your graph, and you check to see if that vertical line hits the graph in more than one place or not, right? And so if the graph that you see intersects any vertical line in more than one place, then it's not a function, okay? And if it happens to be the case that there are no lines where you intersect more than 2 points or 2 points or more, then it will be a function. And we call this the vertical line test, okay? So let's just see some examples of this process looking here, okay? So what you're seeing here are 3 different curves in the plane, and the curves are given in blue. And remember that these are relations, and the reason that they're relations is that all of those points in blue are described by ordered pairs, and we can collect together all of the infinitely many ordered pairs you're seeing there. So this first one is this sort of wavy blue line here. The second one is this sort of parabola-looking shape that's been turned sideways. And the third one is this oval that you're seeing here in the XY plane. And again, these blue points are actually ordered pairs. So these are, just like we had before, a description of a relation. The X values are the inputs, and the Y values are the outputs. So every time that you draw a vertical line like this one here, you're fixing an input, right? It intersects the X-axis at a certain given point. And what you want to guarantee is that every vertical line intersects the graph in at most 1 point. And if it intersects the line the graph in at most 1 point, then it will be a function, right? So for example here, this vertical line intersects the graph in 2 values, this one and this one. And so it's not a function. For this input down here, it's not clear if the output is this Y value up here or this Y value down here. Okay, so this one's not a function. And then this one over here as well, if I draw this vertical line, then I see that it intersects the graph in 2 different spots, and therefore it's not a function. And it's not just this vertical line, it's any vertical line, right? If I can draw any vertical line and see that it intersects in 2 spots, then it's not a function. Okay, so now that I've said that, let's give you guys a chance to think about some of these. So here are 3 different graphs. Some of them are functions and some of them are not. So notice they're labeled A, B, and C down there on the bottom. And again, they're ordered pairs, right? So this whole system here, or this whole blue line that you're seeing is just a bunch of ordered pairs. And one of the ordered pairs that's on here is the X value 3, Y value 0. This one up here is X value 0, Y value 3, and so on and so forth. So these are just collections of ordered pairs. Let me ask you in the chat, which of these are not functions and which are? So let's first start with the ones that are not functions. So A, B, or C? Okay, I like Victoria's answer here. She's clearly spelled out what she thought about A, B, and C. So C is not, right? So C is not. And it's pretty easy to see. If you just look at, for example, the y-axis intersects here at 3 and then also at -3. So we don't know what f of 0 is, right? If we tried to compute f of 0, we don't know if it should be 3 or if it should be -3. Okay, so this fails the vertical line test. And if you fail the vertical line test, you're not a function. Whereas this first one over here, notice every vertical line that you draw, you can see all the vertical lines here. So here's a vertical line, here's a vertical line, the y-axis is a vertical line. Every single vertical line that you draw intersects the graph in at most 1 place, right? There's no places where we have 2 or more intersection points. And you can use that to define that machine that we talked about, right? So the inputs are the x-axis. So for example, you could take as an input maybe -1. And what you want to do then is draw the vertical line that passes through -1, that's this line right here, and see where it hits the graph. So it hits the graph right here. And then you just go over to the y value, and you see that the output of this function at -1 is 3. And that's because it only intersected the graph at 1 point. And so here, what I was saying is that f of -1 is 3, right? So that's how you would write that sort of expression we had there before. So again, that one is a function, and B is a function as well. So B is a line. Let me ask you this quick question. What would be the output for 10 on this line? So the input is x equals 10. What's the output here? Okay. So yeah, you just draw that vertical line, intersects the graph here, and you come back over to the y-axis and you get -2. And if you pass the vertical line test, you could do this for everything in the domain, right? Everything in the domain has one unique output. Okay, so that's how we'll do things sort of graphically. And let's now come back and talk about a relation that we saw at the beginning. Oh, no, let's do a different relation, sorry. Let's do a slightly different relation. And what I want to do with this example is go through all of the different representations of the function to show you sort of the different ways that you can represent the function. Okay, so here we've got this example of a relation that is 2, 1, 3, 1, and 5, 2. Okay? And what I would like you to do is just determine real quickly if it's a function or not. So if it's a function, just type in function. If it's not a function, type in not a function. Okay, great. Everybody sees it's a function because notice the x values, there's no repeats, right? There's a repeat in the y value, but there's no repeats in the x value, so we're fine. And previously, we would have sort of drawn this in the domain range picture here as the inputs are 2, 3, and 5, and the outputs are 1 and 2. So these are the x values, these are the y values. This is what we call the domain of the relation, and this is the range. And again, this relation is the relation S. Okay, so 2 goes to 1. That's what that says. 3 goes to 1. That's what that one says. And then 5 goes to 2. And again, this is a relation because this sort of thing is okay, right? We can have 2 different inputs going to the same output. We just can't have 2 outputs coming from the same input, right? That's the thing that we want to avoid with our function here. But there are other ways to represent this function as well. So this is a function. And one of the ways is to look at it graphically. So to look at the graph of this function in the xy plane. So let's say here's x and here's y. And it would literally just be 3 points in the plane. So the first point here is x is equal to 2 and y is equal to 1. So that's this point right here. That's that first one, and that represents that line. The next one is at 3, 1. So that's this point here. And the final one is at 5, and then a y value of 2. So that would be this point right here. And notice I don't connect the dots at all, right? Because there are only 3 points in this relation. And if you think carefully here, if you draw your vertical lines, right? I'm drawing my vertical lines. Every vertical line intersects this graph in at most 1 spot. Some of them are 0. Some of them intersect nowhere. But we intersect every vertical line in at most 1 spot. So this is a function as well, right? So it passes the vertical line test. I just wanted to show you how you can go from this relation that we were talking about before to something that looks a little more like those pictures that we were seeing. So that's also one possibility. And then sort of the last thing that I want to point out here is that the book and many applications of functions in the real world, so those of you who are maybe not necessarily going on to calculus, but may see functions in other places, will often see them in a tabular format like this. So you'll list the inputs here, those are the x, and then the outputs down here. And this is just going to list off those order pairs in a tabular form. So the inputs are possibly 2, 3, and 5. Those are the various inputs. And then right below the input, you write the output. So here the output of 2 was 1, the output of 3 was 1, and the output of 5 was 2. And the fact that there's no repeated x's up here means that it's a function. And they'll give you some examples like that as well, right? So instead of listing out the ordered pairs, they'll give it this way, they might give it this way, or they might give it in terms of an actual graph. So there are a lot of different ways. And as we've seen before, you can also write down just an equation, right? So an equation can be used to describe a relation as well. And the one that we looked at was this y cubed plus x squared was equal to 1. Okay, so that's that first objective. How do we determine if something is a function? And now we want to hit our second objective using function notation. And in terms of the Affinity homework assignment, there are, I think, at least 10 or 12 questions that are asking you to use this function notation correctly. So let me give you some examples of that. And we've already talked about this, but this is just formalizing it a little more. We use the following notation, y equals f of x, so that's what I had written on the board at the beginning. We think about it as the function f, so that's defining the function f. This isn't f times x, it's the function f evaluated at x. We say that y is a function of x when we write something like that down. The x's represent the input, and the y's represent the output. And the y is the f of x, okay? So this is the notation that we'll use, and it's pretty good notation because instead of drawing these pictures or these graphs that we had before, we can do things like the following. We can just say something like f of x is equal to x squared plus x plus 1, right? This is an example of a function defined using function notation. You give me the input x, and the output is just square x, add it to x, and then add 1 to that. And that's that machine that it's going to get you the output. So we have to be pretty familiar with this notation because the further sections that we look at have a lot of questions or a lot of stuff that depends on being able to evaluate a function. So let's go through and do some examples like you might see in Affinity. So let's let f of x be equal to the absolute value of x minus 8 minus the absolute value of x plus 2. And what we're going to do here is going to evaluate this at a bunch of different points. So we want to compute f of negative 2. We want to compute f of 1. Those are pretty straightforward because they're just putting numbers in, so you're going to get a number out. Something that's a little bit harder for students is what happens when you put a variable in. So we'll also input variables. So we'll compute things like f of a. We'll compute things like f of a plus h. So this means plug in a plus h into the function. We'll want to look at f of negative a. And we're going to see that it's not the same thing as negative f of a. This is not multiplication, so you can't pull that negative sign out to the front, okay? They're going to be different from one another. And like I said, there's like, I think 6 or 7 questions in Affinity that are of this format, right? They give you a different function, and they want you to evaluate. So what we're using here is the function notation. It's a pretty straightforward process. For example, this first one, what it means is you take your x, and everywhere that you see an x in that formula, you replace it with negative 2. Okay, so now that I said that, let everybody plug it in and see what you get for your output when you plug in negative 2. Alan, so again, what we're going to do is everywhere that you see a negative, an x in this equation, you want to plug in the negative 2. Okay. Jordan comes in with 10. Okay. So the answer is 10. You have to be careful with the absolute values. So let's go through and do this. So everywhere that you see an x, you plug in negative 2. And then from there, you just sort of go through the process of simplifying. So plugging in the negative 2 is like throwing it into that box that we said. And now we're going to chug through the computation. And eventually what we want to do is get out the output, right, which is represented by f of negative 2. So here, negative 2 minus 8 is negative 10. And we still have that absolute value. Over here, negative 2 plus 2 is 0. So it's the absolute value of 0. Now I'll evaluate the absolute values. The absolute value of negative 10 is 10. The absolute value of 0 is 0. And so this is all equal to 10. So for the input negative 2, the output is 10. Now what does this mean graphically? Well, for this function, the point negative 2 for the x value and 10 for the y value is on the graph. Okay? So this is on the graph of f of x. Okay? Go ahead and plug in 1 and see what changes. So what do you get when you plug in 1? And once you have your answer, type it into the chat. So now we're going to plug in, I'll do it in a different color here. We're going to plug in 1 now. Okay, so it looks like everybody's getting 4 in this case. So let's see why the answer is 4. So everywhere you see an x now, you'll plug in 1. So instead of the -2 here, you're plugging in 1. Instead of the -2 there, you're plugging in 1. And then you just go through the whole process that we went through before. So 1 minus 8 is -7. And that's the absolute value of -7. And then over here, this is minus 1 plus 2 is 3, and that's the absolute value of 3. The absolute value of -7 is 7, and the absolute value of 3 is 3. So we really get 7 minus 3, which is 4. Okay, now graphically, it means that the point 1, 4 is on the graph of f of x. And if we were to graph all of the points on f of x, it would pass the vertical line test because it's a function, right? For every input x, there's a unique output given by that formula. Okay, so those are sort of these ones where you just plug in numbers and you simplify things. For students, it gets a little more difficult when you have a variable, and it's primarily because in some examples in Affinity, they'll ask you to simplify things. So you should read the question carefully. If it doesn't ask you to simplify, it's really easy, right? You don't have to multiply anything out or simplify the algebra or anything like that. And in this case, they're not asking us to simplify anything. So here, we're going to look at f of a. And all it means is that everywhere we have an x, we're going to plug in a. So it would just be the absolute value of a minus 8 minus the absolute value of a plus 2. Everywhere you see an x, replace it with a. And this is what Affinity would accept as the right answer. There's no need to simplify anything or multiply anything out because it's not asking you to simplify. If it says simplify, then you should. This one wouldn't simplify, but there are some where you might have to FOIL things out or things like that. Okay, so f of a plus h is just the same thing, but now we're replacing x with a plus h. So here I get a plus h minus the 8 and then the absolute value. And then over here I get minus a plus h plus 2 and then the absolute value. Those of you going on to calculus, this is really important, right? This f of a plus h and f of a are going to show up all over the place in those courses. So being able to evaluate at a variable, you'll use that, I think, in the first 2 or 3 weeks of Calculus 1. So that's a really important part of that. Now let's talk about f of negative a and f of a. I'm sorry, f of negative a and negative f of a. These are two different things, right? The first one means plug in for every x negative a. So here, I'll get negative a minus 8 minus negative a plus 2. Okay, that's replacing every x with negative a. On the other hand, this one, the negative sign is not on the input, it's on the output, right? And again, this is not f times a, so these two things are not the same, right? This is not f times a, this is f of a. And this one means negative 1 times f of a, okay? So here we computed f of a. So all we have to do is multiply this by negative 1 on the outside. So negative f of a is just going to be a negative, and I'm going to put in parentheses here, the absolute value of a minus 8 minus a plus 2, close the absolute value, and then close the parentheses. And if it's not asking you to simplify, this would be good enough in Affinity, right? This would be accepted as the right answer. Now, if it's asking you to simplify here, I would say distribute the negative sign, so that makes this one positive and then a negative over here. But after that, there's nothing else you can do to simplify. And there are a lot of questions like this. This will come up again for us as well, because what we'll find is that when these two things are the same, the graph has some really nice symmetry in it. It's called odd symmetry. And we'll talk more about that later in chapter 3. Okay, so coming back to the slides, I want to talk a bit about function notation really quickly. And this has a duplicate in it, so this thing down here is the same thing as this up here. It's a pretty easy how-to, right? So given the formula for the function, what do? You replace the input variable with the value provided, and then you calculate. And what they mean by calculate is just sort of simplify as much as you possibly can. Okay, so important, especially when you're dealing with variables, right? The a plus h or the negative a, that sort of thing. Okay, I also want to talk about a slight variation on this problem that you'll see in Affinity as well. So let's do that. And what they'll ask you for is, given a certain output, what possible input led to that output? So here's the type of question that you'll see. So let's let f of x be just a really simple function, 5x minus 1. So you give me the input x, it multiplies by 5, and then whatever it gets after multiplying by 5, it just subtracts 1. So that's what that machine is doing to a given input. And here we want to evaluate f at -3, and we'd like to solve the equation f of x is equal to 10. Okay, and notice that these are two different things. This one's evaluating the function, and this one's trying to figure out what input x would give you the output of 10. And it may be the case that there's no solution, right? It could be that there's nothing that gives you an output of 10. But we should be able to figure that out using some algebra. Okay, so the first one is pretty straightforward. We just replace the x with the input, which is -3 in this case. We get 5 times -3 minus 1. 5 times -3 is -15. -15 minus 1 is -16. Okay, so for the input -3, the output is -16. Okay, and then the second question here is asking us what input will give us 10. So to do that, we just set up an equation. We replace the f of x with the equation, and we get 5x minus 1 is equal to 10. And then we just solve that equation for 10. So you add 1 to both sides, you get 5x is equal to 11. You divide by 5, and you get x is equal to 11 over 5. And what it means is that if you were to plug in 11 over 5 into this formula, you would get an output of 10. Okay? So that's another variation on a question that you'll see in Edfinity. And let's now finish up with talking about one-to-one, and then we'll look at our sort of library of functions that you should sort of know the shape. So adding on one-to-one just means that in terms of the relation, that the y values don't appear more than 1. So previously we were saying for a function that you can't repeat the x value in the set of ordered pairs, but if you also don't repeat the y value, you get something that's a one-to-one function. And the reason why we would be interested in one-to-one functions is that when we do that, it's possible to replace the x and the y, to swap them. And when we swap them, we get to the idea of the inverse of a function. We'll talk more about that later in chapter 3. But what I want to point out here is that there's a corresponding horizontal line test, right? And the horizontal line test is our method to determine if something is one-to-one. So what does the horizontal line test say? It says the following: if you intersect every horizontal line in at most one place, then you're a one-to-one function. If there is a place where you intersect a line in more than one place, then you're not one-to-one, right? There's a repeated y value. There's no questions like this in Infinity, so I'm not going to do an example, but we will see it again when we talk about inverse functions. Okay, so that's the one-to-one business. And now we'll move on to just discussing a few functions that you'll sort of need to know the shape of. And this is sort of the first introduction to it, but later on we'll be translating these functions around. So we'll move the graphs up and down, left and right, we'll stretch them and squeeze them. So we'll have lots of different methods for transforming these. But the ones that you need to be familiar with are constant functions. So a constant function just has the same output for any given input, okay, where c is just some number. The picture you're seeing here on the right is the constant function where c is 2. So you give me any input whatsoever, and the output is 2. Now, what does that look like graphically? Well, the point -2, 2 is going to be on there. That's this point. The point 0,2 is going to be on there. The point 2,2 is going to be on there. And basically, any x value with a y value of 2 will be on there as well. So that's this entire blue line. So any function of the form f of x is equal to a number turns out to just be a horizontal line, and it passes through the y-axis precisely at the value of c, in this case 2. So this is the function f of x. See if I can write that here. F of x is equal to 2. Okay? So that's a constant one. Another one that we'll have to sort of be familiar with the shape is what happens for an absolute value. So the absolute value function, whenever you plug in a positive, just gives you the same value. So for example, at 2, you get an output of 2. At 3, you get an output of 3. At 4, you get an output of 4. And so at 0, you get an output of 0. And so on the right-hand side here, on the x-axis, you just get a line that goes up and to the right? And it's the line y equals x, basically. However, on the left-hand side, when you plug in -1, you get 1 instead of -1. So it starts to go up as you come to the left-hand side. At -2, you get 2. That's what this point is here. X is -2, the output is 2. The input is 0, the output is 0. But these negative ones give you positive values, and so you go up in this direction. And so the general shape here is a V shape where this has slope -1 and this has slope 1. So that's the general shape of the absolute value function. And again, you can always think about these in their equation form, in their graphical form, or in their tabular form, right? So we're seeing 3 different formats for this absolute value function. Okay, so another one that comes up often is a quadratic. A quadratic has this sort of x squared in it. So you take an input, and to get the output, you just square it. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And so as we go to the right, we grow, but faster than a line, so it looks like this. And we go to the left, we also grow, getting larger, so we go up as well. This shape here is called a parabola. And these points that you're seeing in black are just the points that you see over here. So again, we've got the formula, the graph, and then a table version. And the most detailed ones are the equation and the graph, because all of the information is there. The table is missing some of the information, right? So we don't know what happens, for example, at 1.5 if we're just given the table. These guys are called quadratic, and I should say that anytime you have x to the power of n, and the n is even, it'll look like this. So they look like quadratic functions for those. When the power is odd, for example, x is to the power of 3, then when we plug in negative numbers, like -1 times -1 times -1 is actually still a negative. So 3 negatives in a row still makes a negative. So as we go to the left, this thing drops down instead of going up. And then when we go to the right, you plug in a positive and cube it, you still get something that's positive, so you go out to the right. For example, 1 cubed is still 1. So it has this sort of nice S shape to it. And I want to point out that this guy is 1-to-1. I'm sorry, is not 1-to-1. It doesn't satisfy the horizontal line test, but this guy is. The horizontal line test is passed here. Every horizontal line intersects this graph at most one point. These guys are called cubic. And anytime that you have something that is 1-to-1, it will also have an inverse. And the inverse is sort of the method that we use to undo this x cubed, right? So how do we undo x cubed? With cubics. How do we undo squares? With the square root of x. And you'll notice that this just looks like that graph sort of turned sideways for x cubed. We're going to talk more about this idea of inverses, and that's where this idea of 1-to-1 will become really important for us. For now, it's just sort of a definition. Okay, so that's all I wanted to talk about. Just as a reminder here, we need to determine whether a relation represents a function, and this is tough because there are many ways to represent a relation. We need to evaluate functions at a given value, lots of practice at infinity, and you need to be good at this for further courses. We didn't really say much about 1-to-1, so I wouldn't worry too much about it. We'll bring it back up again later. You should be able to use the vertical line test to identify when a graph is a function, so that's getting back to this first objective. And then finally, we had that list of sort of graphs, and we'll be adding more things to it as the semester goes on. Okay, guys, thank you guys for being here today. And again, we're going to cover 3.2 and 3.3 on Friday, and don't forget to start that homework assignment.